Well, welcome everybody to the Royal Society Centre for the History of Science, and so this is the first of the autumn series of lectures. We have a great programme over the coming year, and I hope we'll see such a wonderful full house in the future. So welcome, a very, very warm welcome to you. My name is Jonathan Ashmore. I'm Chair of the Library and Archives Committee. It's my great pleasure today to introduce the first speaker, Sir Arnold Wolfendale, to give his lecture. So, Sir Arnold is an astronomer with a very, very distinguished career. He was educated at Manchester University, and then after briefly taking up a position at Manchester, moved to Durham, where he's remained ever since. He ran the Department of Physics at Durham University, and in 1991 to 1995 was Astronomer Royal, a position which I'm sure people in this room know was a position which descends from a position appointed by Charles II to John Flamsteed in 1675. So Sir Arnold is currently an emeritus professor there in the department, and it's perhaps appropriate that today's lecture takes place on an astronomically very significant day, of course, the autumn equinox, with deep astronomical and cosmic undertones. And so it's my great pleasure to introduce him to tell you about 100 years of cosmic rays, Sir Arnold Wolfendale.
Thank you very much for the introduction and for the applause. It's always nice to have it at the beginning. Don't always get it at the end. People don't like what you say, but I think you will appreciate it anyway, some of it. We all know the story of Marie Curie and her work on radioactivity. Very, very important work. And of course there were others as well in this time frame, people like Becquerel and so on, who worked on radioactivity. But there was a problem. When they had their detector of radioactivity, say this is it, and they took the radioactive source away, they were still getting a small reading. Some radiation was affecting the detector. And no matter how much lead they put round it, there was still a small reading. And here, then, we have a perfect example, as we shall see, of some tiny anomaly, if you like, some tiny physical phenomenon that led to much, much greater things. So electroscopes always lost their charge, another way of putting it, even when they're shielded. Why was that? Well, 100 years ago, last month, in fact, this man, Victor Hess, and two colleagues, a balloonist and the meteorologist, went up in a balloon, and he, although you can't see it, he was carrying an electrometer, gadget for measuring ionization, measuring radiation. Because he argued that if he went up, up and up and up, then if the reading went down, then the source of the radiation must have been on the Earth. Some funny sort of gamma radiation. Gammas were known, alpha, beta, gamma. They were known at that time. So he argued it should go. People had tried it, gone up the Eiffel Tower, for example, but with ambiguous results. But he was an ardent balloonist, and he succeeded, as we shall see. August 1912, hydrogen-filled balloon. Anyone here from the Health and Safety Executive? Can you imagine it? Hydrogen-filled balloon, 17,600 feet. There was some oxygen, which he had. That's the thing about the scientists. You know, if there's anything going, they will get it. But this bloke, Major Hoffrey, the balloonist, he didn't have any. Now they did the meteorologist, apparently. But that's hard luck. The balloon started from Austria, and landed in Germany, Berlin, near Berlin. And to celebrate, earlier in the year, we had a conference in Austria, near where he set off. And a few weeks ago, to coincide with the landing, we had a conference near Berlin. It's good to have an excuse. See, usually you've only got an excuse for one conference in the place where the discovery was made. But since it was made up there, between here and here, good excuse to have two conferences. Right. What did he find? What did they find? They found this. Here is the height, the altitude in kilometers, and this is the reading on their instrument. And you see, these are two ionization chambers they're detected. Initially, it went down. But then, above 1 kilometer, it started to go up. Started to go up. And he had 3 flights, and he got the same result each time. He was an atmospheric electrician. There were a lot of people interested in electric fields in the atmosphere. Things like lightning, phenomena of that sort. So he had no preconceived ideas, but he said it is coming, it is a radiation, a cosmic radiation coming from outside. And he was right. We're not always right. What could have happened was that it was a so-called ionosphere, because up above this height there's a region of the atmosphere which is ionized, where the atoms have had their electrons knocked off. And I think if it had been me, if it had been most scientists, and they'd seen something coming from above, they would say it was associated with that layer. But it wasn't. He was right. It was extraterrestrial. This was followed, this work, that was 1912, was followed in 1913 and 1914 by a German scientist who went even higher, as you can see, and he reproduced this result. It was shown, and this is part of the showing thereof, it's not a radiation at all, it's a beam of atomic particles, mainly hydrogen nuclei, protons with a couple of % of electrons, and some even heavier nuclei. So the term cosmic radiation is a misnomer, but it's stuck. It's not uncommon. It's stuck. And this is one result that tended to confirm that idea. This shows the ionization, if you like, of the counting rate of the detector against the latitude. This is the region of the equator here, and here, well, the pole, North Pole will be up here, and the South Pole will be down here somewhere. And you see there's this dip. And this happens, and this is the dip at a different depth. This happens because the particles, cosmic particles, are charged, and the Earth has a magnetic field, doesn't it? North, south, east and west and all the rest of it. And the field is directed so that the lines of force come into the poles, so that particles coming from elsewhere, high energy particles, tend to be funneled in along these lines of force. So you get more out here and out here than you do here. Here, at the equator, and this is geomagnetic, but it doesn't matter, they are deflected away. And the Earth's magnetic field is very important in shielding us from many of these particles. If one goes to northern latitudes at night in the winter, you can see the aurora. Now, this is interesting. This shows the cosmic ray intensity from balloon flights. Here we go again, balloons. this is the intensity, and this is the equivalent depth in meters of water. It's a bit confusing, but this is the unit that people use. So ground level will be down here somewhere. And as you go, imagine going up in a balloon now to a much greater height. The intensity goes up, 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 up. It reaches a maximum at a height corresponding to about 20 kilometers. And what happens is that the cosmic ray particles come in to the atmosphere, and if they have very high energy, they will multiply, if you like. They will hit the atomic nuclei of the air, oxygen and nitrogen, break it up into many, many particles. So many of these are the secondary particles. The first high-energy cosmic ray particle recorded or published, at any rate, was by a Russian, Skobeltsyn, using a cloud chamber. Now, many of you will have heard of cloud chambers, a device often cylindrical, containing oxygen and some alcohol to give a vapor. And if you expand it suddenly, then the air is clean, oxygen is clean, etc., you get droplets of water on the ions, on the track of the particle. So here, these things, they're curved because the cloud chamber is in a magnetic field. Magnetic field. I remember when I was a student, Blackett, a great man, came to see our cloud chamber. And he had his metal spectacle case in his upper pocket. And he leant forward to tap the glass for some reason. And this thing shot out and nearly broke the cloud chamber. Whose fault was that? Mine. I should have warned him. But in addition to the tracks here, circular tracks, because the particles are reflected into circular pathway there, you can just see a cosmic ray that came in by chance. By chance. You see it going down here. Rather faint down at the bottom. You see that? The very first cosmic ray. And you can see that it must be travelling much faster than these, because the radius of curvature is small when the energy or the momentum is small, and it's big. So that these cosmic rays already, it was realised their energies were much higher than those from atomic material from atoms, from radioactive atoms. One of the most important early developments, and this is 1933, was the discovery